এভরিথিং হচ্ছে না, শেয়ার করতে পারছে না,
ক্লিক করে গেল।
ফায়ারফক্সের স্ক্রিন বসে Yeah, it has come now.
Can you see my slides?
Yes, yes,
And you can hear me?
yes.
Good. Thank you.
টাইমটা দেখো, খেয়াল করো, 10:20 বাজলো তো, এই টাইমগুলো অনেক
Can you see my pointer? No?
Yeah, we can see the pointer.
Oh, good, good. Since my pointer is not shown on this Google Chrome.
Can you just do it once more?
I move the pointer on the PowerPoint, but can you see my pointer?
No.
Okay. So what to do? Yeah, but it's all right.
Yeah, I think it's fine. There is no problem. It's visible.
Okay. Thank you.
Sir, can you please change the slide so we can see if the slides are actually changing or it is frozen or not?
Yes. Like this?
Yes, sir.
Yes, sir. It is.
Okay, sir.
Well, so let us start the proceedings today. This is the second day of the conference FPGP 2022, and today's first speaker is Koji Hashimoto from Kyoto, and this is an invited talk of 40 minutes, and he will be speaking on an energy bound on chaos. So, Professor Hashimoto, it's all yours now. You may start at this point.
Okay, yes. So let me start. So first of all, I'd like to thank the organizers of this workshop. I wanted to visit India, but now, unfortunately, also in Japan, it's in the middle of a pandemic. But in the future, I like to visit India again. Uh, so let me just say namaste, and I'd like to start my talk. So the topic of my talk is chaos, and I think most of you have heard of this bound. This is the first page of the famous paper by Maldacena, Schenker, and Stanford. It was about a proposal of a bound on chaos. And as you can see, this actually sets a very nice upper bound on how chaotic the physical quantum systems are. And the bound is written here. The Lyapunov exponent, which characterizes chaos, is upper bounded by this number, which is proportional to temperature. And this bound is applied to, for example, quantum system with large n degrees of freedom. And this particular bound was very useful to discriminate whether quantum field theory can have a gravitational description or not through the holographic principle. So in that sense, this bound was quite nice. However, there is one shortcoming of this bound. what I would say shortcoming is that, for example, this bound, the right-hand side is divided by h bar. So this means that when you take a classical limit, h bar goes to 0. So there is no bound. So right-hand side diverges. So this means that this bound is applicable only for quantum case. And also, as is particularly shown in this abstract of Maldacena, Schenker, and Stanford, this applies to only the system with a large number of degrees of freedom. So this means that, for example, if I consider just a single particle quantum mechanics, then this bound will have no meaning. And also, if I consider just classical mechanics, possibly with large number of particles, unfortunately, this bound does not make sense, since this bound is only for quantum case. So here in my talk, I'd like to generalize this kind of Maldacena, Schenker, Stanford chaos bound to more general cases. More general means that it can be applied to, for example, single particle mechanics, and it can be applied to classical mechanics. Okay. The work has been done in collaboration with Murata and Tanahashi and Watanabe. They are in Japanese universities. But this, our conjecture on the new energy bound on chaos was already written in this paper, which was published 5 years ago in Physical Review Letters. It was just a footnote, so nobody noticed it. But we elaborated on this footnote, and here I claim that this bound is quite generic, and it can be applied to any physical system in the universe. So, okay, let me start my talk. So here is the conjecture. It's clearly stated, and it's very easily understood. So I think you can, in fact, remember the content. But let me read this conjecture. The essence of this conjecture is that any chaos is characterized by Lyapunov exponent, and this Lyapunov exponent does not grow faster than linearly in energy in the high energy limit. So this is a statement. So I think the common sense in the analysis of chaos and nonlinear physical systems is that if you put arbitrary complication of potential or nonlinearity in the system, then you can make it arbitrarily complicated. I think that's a common sense. So that's how the standard in the case. I think it's the standard way to think about physical systems. However, here we mean by this statement that how chaotic the system is actually bounded from above, and it is characterized by energy. Of course, energy is the most important and conserved quantity in any Hamiltonian system. So anything can be characterized by energy. So Lyapunov exponent itself is characterized by energy. And now, suppose that the Lyapunov exponent is measured for a certain energy. Okay, so you can see. So I will make a brief review about the chaos and Lyapunov exponent later. But let me make a statement of this conjecture first. Suppose you consider some system, any system of your interest, and measure the chaos by measuring the Lyapunov exponent. Lyapunov exponent is a function of energy. Then this conjecture says that the energy dependence of this Lyapunov exponent is just by characterized by e to the power of c, where c is bounded from above like this. Okay. This is a very simple statement. And so later I will tell you how this conjecture was kind of physically derived, and I will explain the motivation for this. But before that, since we have noticed this conjecture 5 years ago, and we checked whether chaotic systems actually satisfy this or not. And surprisingly, all the cases which we checked, the Lyapunov exponents satisfy this bound. So this is just an example of those physical systems which are known to be chaotic, classically or quantum mechanically. Example includes double pendulum. So this is a very famous chaotic system, or HH system, a particle in black hole geometries, nonlinear sigma models, film pasta Uran beta model, large and coupled rotors, chaotic string in ADS geometries, homogeneous Yang-Mills mechanics, and Yang-Mills theories on lattice, and many chaotic systems. So there are plenty of papers which measured the Lyapunov exponent for each case. And we checked the energy dependence at the high energy limit, and we found that this conjecture bound is satisfied. So it was a kind of striking to me, since I thought that chaos has no bound. So Maldacena-Schenker-Stanford's bound was incredible in a sense that it sets some upper bound, but it was limited to a certain case where it needs to be quantum and it needs a large number of degrees of freedom. But here, this conjecture applies to any chaotic system, classically or quantum mechanically, and single particle or large N. Yes?
May I have a question? Yeah, hello. When does it saturate this bound?
That's a good question. I can say that when the Maldacena-Schenker-Stanford bound is saturated, then this bound is also saturated. Yes. So in that sense,
for gravity, they would be saturated.
yeah, that's right. So when the system allows gravity dual description, then this bound is saturated, and also Maldacena-Schenker-Stanford bound is saturated.
Can I interrupt you, Professor Hashimoto?
Please.
Is it possible that the C also becomes a function of energy?
Yes, but it's subtle. For example, if this Lyapunov exponent is proportional to log of energy, then you would say that the C is dependent on energy, right? It's a way of writing this thing. Yeah, but so I think in the standard case, if this Lyapunov exponent is written as a power of energy, since Lyapunov exponent has a dimension, and normally coupling constant has a dimension. So if Lyapunov exponent is written by a coupling constant, then coupling constant depends on energy, and that is the energy dependence of Lyapunov exponent. I don't have a good answer, generic answer to your question, but here, yeah, for most of the cases which we have checked, this is a function of energy as a power function.
Thank you very much.
Thanks.
Yeah, there is one more question. Jeff, you can go ahead.
Yeah, thank you. Hi, Koji.
Hi,
Just a question. This is a statement about the leading Lyapunov exponent, yes?
what do you mean by leading?
So in a classical system like the double pendulum or Henin-Hales, for example, there's a spectrum of Lyapunov exponents. And usually statements are made about the leading, the biggest Lyapunov exponent. So the bound that you're talking about is the bound on the leading Lyapunov exponent.
Yeah, it's a much small Lyapunov exponent, yes.
Okay. For these classical systems, can you say anything about the further exponents? Is there anything to be said about the spectrum of Lyapunov exponents?
Well, no. So here, so this conjecture is about large energy, high energy limit. So this means that at high energy, of course, the maximal Lyapunov exponent is growing rapidly as a function of energy with the maximal C. So this says only about the maximal Lyapunov exponent.
Thank you.
Okay, so I think I motivated you enough for this conjecture. And yeah, this is a very good occasion for you to advertise this conjecture. If you find any example of chaotic system which actually violates this bound, please let me know immediately, okay? That's very important for us. Okay, so my talk is divided into 3 parts. First, I'd like to explain my motivation so this is a review part, black hole and chaos. And I will say a little bit about how this conjecture is physically expected. And in section 2, I'll tell you some non-trivial examples, which is just a classical mechanics, and I can argue, in fact, concretely, how this bound can be understood in those classical examples. And finally, section 3 is just for discussion, what this conjecture implies and how this conjecture can be used, and what are the physical conditions for this conjecture to be true. So let me start with section 1. Section 1 has 5 slides. First, I'll explain what the definition of normal chaos, classical chaos. That is about sensitivity to the initial conditions. And then section 1, 2, I'll explain quantum chaos and Mardisna-Shenker-Stanford chaos bound. And in section 1, 3, I'll explain how black hole horizon is consistently understood as a saturation of Mardisna-Shenker-Stanford bound. And using this Mardisna-Shenker-Stanford MSS bound, in section 1, 4, I'll tell you how to look for black hole-like quantum mechanics. This means that suppose you have some quantum mechanics, and whether you want to check, so you want to check whether this quantum mechanics allows gravitational description or not. Then you use this MSS bound and check the chaotic Lyapunov exponent and see how it saturates the bound or not. So this is how you look for black hole-like quantum mechanics. And in the computation of this Lyapunov exponent, in fact, there is a subtlety appears. And our conjecture is originated in this subtlety of computing the Lyapunov exponent for quantum systems and classical systems. So this is section 1.5, and here I explain why this conjecture is expected for physically reasonable systems. So let me start with section 1.1. So from 1.1 to 1.4, this is just a review, and 1.5 is the explanation of the conjecture. So what is classical chaos? Classical chaos is the statement that non-periodic bounded orbits, which are sensitive to initial conditions in nonlinear deterministic dynamical systems. So this is a sharp statement. And how chaotic the classical system is measured by a so-called Lyapunov exponent, lambda. So this lambda appears in the motion in phase space. Suppose you start from one point in the phase space, and then this time evolves along this orbit, like this. And suppose you slightly change the initial condition to here, then time evolution goes like this. And if the distance between these two in the phase space grows exponentially in time, then you can say that this system is chaotic. Since if you measure things around here, if you measure things around here and if you measure things around here, then if the slight difference at the initial point grows exponentially in this way, then you lose the information about the initial condition. So the system is quite sensitive to the initial condition. Lambda is 0 for solvable systems, and lambda is positive for chaotic systems. So this is the example of the plot of the Lyapunov exponent lambda for stadium billiard. Stadium billiard means that you have a boundary, Dirichlet boundary condition of this shape, and you put the particle inside, one particle, and then let the particle moves. It bounces on the boundary, and this motion, from this motion you can measure the Lyapunov exponent. A and R is the size of this billiard, and as a function of A over R, this Lyapunov exponent changes like this. Okay, so this is the Lyapunov exponent. Now, the quantum version of this Lyapunov exponent is measured by a so-called out-of-time order correlator. This was a major breakthrough in ADS-50 correspondence in around 2015. And one of them is, of course, ignited by this Mardisna-Shenker-Stanford paper. So this out-of-time order correlator, if this combination correlator grows exponentially in time with the coefficient exponent lambda, then you would say that this quantum system is chaotic. And lambda is quantum Lyapunov exponent. Why this out-of-time order correlator is important? The classical analog is quite easy. If we replace this xt and p0 by the commutator of xt and p of 0, then you can write this as this, where differentiation with respect to x of 0 means the commutator of by p of 0, right? So this out-of-time order correlator corresponds to this combination, which grows exponentially in time when the system is chaotic. So this is why this out-of-time order correlator is important in quantum chaotic systems. And as I already said, this MSS bound exists for quantum and large n system, where the upper bound is given by 2 pi t over h bar. And the point is that here temperature appears in the right-hand side, which means that the correlator, the out-of-time order correlator, needs to be measured at finite temperature rather than energy. So this correlator, you need to specify how this expectation value is taken, but this is the thermal correlator. Okay, so this is the review of quantum chaos and its bound by Maldacena, Shenkan, and Stanford. Now in the next slide, I'd like to explain why this is expected for the system which allows gravity law description in ADS-CFT correspondence. In ADS-CFT correspondence, non-gravitating quantum field theory has a dual description in the gravity which has one higher spatial dimensions. Originally, Shenkan and Stanford studied shockwave delay by the injection of another particle into the horizon. So the physics is something like this. So here I draw a Penrose diagram with the horizon here and ADS boundary here. So this is the ADS black hole Penrose diagram. Suppose you consider a particle which flies very close to the horizon and reaches the ADS boundary at time t2. And now you consider another particle which is injected into the horizon and it leaves the boundary at time t1. And then because of this energy of this second particle which goes into the horizon is made a little bit fat compared to the original horizon. So this red dashed line is the location of the horizon after it absorbs this second particle. And because of this shift of the horizon location, the time which the first particle arrives at the ADS boundary can change. And this is just a red shift. And the red shift created by this change of the horizon location. And in 2D Diraton gravity, which is supposed to be dual to SYK model, in particular, Armeli Polchinski and Fairlinde and his collaborators computed this time shift and reached this kind of result, where the time difference due to the injection of this second particle is given by exponential of 2 pi temperature T2 minus T1. And this temperature is the Hawking temperature of this black hole. Okay, so this redshift factor is quite easy to understand. However, the point is that this is exponentially dependent on T2 and minus T1. And in fact, the coefficient in front of this exponent should be understood as a Lyapunov exponent. So that's why in the generic gravity systems, the Lyapunov exponent, due to the surface gravity of the black hole horizon, is given by the Hawking temperature. There is another way to understand this Hawking temperature Lyapunov exponent. So suppose you consider some generic static black hole, and this is the radial direction of the black hole. If you put a particle outside of the black hole, then of course it gravitationally falls down to the horizon. So consider some repelling force which you put to this particle so that it does not fall into the horizon. Okay, so this force can be electromagnetic or any other force you can consider. And this particle goes very near the horizon, but it does not go to the horizon. So that so you pull out this particle so that it does not go into the horizon. So the system is given by this Lagrangian. The first term is a particle Lagrangian with the black hole background, and the second term is some potential which you put by hand so that this particle does not fall into the horizon. And we expand this expression for any v of x near the horizon, then you find that, in fact, the particle potential near the horizon is approximated by this inverse harmonic oscillator, whose coefficient is given by Hawking temperature. And this means that there exists a separatrix very near the horizon. So here is the horizon, and here is the separatrix, which characterizes the exponential growth of the particle motion here. So the separatrix is described by this Hawking temperature. So Lyapunov exponent is Hawking temperature. So this is the intuitive reason why in the gravitational system with the horizon, you expect Lyapunov exponent, which is proportional to the Hawking temperature. Okay, so here, suppose you want to find a quantum system which may have a gravity dual. Then here is a protocol to follow to find a black hole-like quantum system. So first, you prepare your favorite Hamiltonian, then you solve the energy eigenstates. You get like this, and using this energy eigenstate, you calculate the out-of-time order correlator like this. Since this is with the energy eigenstate, you can call this microcanonical ODOC. Since the MSS bound is for thermal ODOC, you need to convert it to thermal ODOC like this. So here F is the microcanonical ODOC, and then rho is the density of states. And then you make an energy integral, then you get thermal ODOC. If this thermal ODOC grows exponentially in time, then you can get the Lyapunov exponent. The thermal Lyapunov exponent is given by logarithm of this thermal Lyapunov exponent divided by divided by t.
Excuse me. Even within the microcanonical ensemble, you can define the temperature from the entropy, which is a function of the energy. So you don't need to go to a canonical ensemble, right? Question is, do the answers match if you do that?
That's a good question. In fact, when the system allows infinitely many degrees of freedom, then you can do it. Yeah, that's right. So energy is almost equal to temperature. But when you consider just one particle system or two particle system, then you cannot do it. Okay.
Yeah, okay. The question is, in a microcanonical ensemble, of course, you have an isolated system. It's an isolated system where the energy is the only determinant. There's no heat bath which couples to your system.
That's
right. Therefore, you should be able to determine everything in principle. Of course, practice may be different, but in principle, you should be able to calculate the Lyapunov exponent. At least there should be a formula, right?
So I don't understand quite well your question, but here the point is that the MSS bound itself was written as a thermal ODOC, thermal Lyapunov exponent. So to compute the thermal exponent with some heat bath, then if we start with the isolated system, then
yeah, so the MSS bound is dependent on a canonical ensemble. That's canonical ensemble treatment. All I'm saying is you can also do a microcanonical calculation and check if you get the same Lyapunov exponent. All in statistical mechanics, all canonical microcanonical ensembles, equilibrium ensembles should lead to the same physical results, right?
As a total, I think I understand. I agree with you. But my motivation is actually coming from this protocol. There is a subtlety in this protocol, in particular this number 3. So let me tell you that first to you.
Okay, thank you. Thank you.
Please. Yeah. So in this third part, in fact, there is a subtlety. This part. So here I assume that this energy integral is convergent. But if this microcanonical OTOC is a bad one, then energy integral does not converge, right? Yeah. In fact, when the microcanonical Lyapunov exponent, which appears in this microcanonical OTOC, exponential of lambda t, this lambda grows faster than linearly in energy, then this integral does not converge. So you cannot go to canonical. I think all of you agree. This is a very simple manipulation of the equation, integral equation. So from this, so if I demand that this thermal OC can be defined, or rather to say, the well-definedness of canonical ensemble for out-of-time order correlators, all possible out-of-time order correlators, then I need to expect this energy bound, which is the Lyapunov exponent growing as a E of C, where C exponent needs to be smaller than 1 or equal to 1. Agree? I think you agree. So this is a very simple consequence of how we can go from microcanonical to canonical consistently for the case of out-of-time order correlators. So previously we considered only time-ordered correlators. Then there is nothing wrong about that. But here, if you consider out-of-time order correlators, then it exponentially grows. That's the point. If it grows exponentially, then there is a subtlety in converting it to canonical ensemble. Okay, so this is the explanation of the conjecture. And now I go to section 2. I have 10 minutes. So I may explain section 2, and that's it. But yeah, let me go to section 2. Examples of classical mechanics. So you remember that MSS bound does not apply to classical mechanics, since it includes h bar in the denominator. So if h bar is taken to be 0, then MSS bound does not have any bound. But here, my case, of course, applies also to classical case. So we expect that this bound can be seen in any classically chaotic system. In section 2, I have 4 slides. First, I will explain general billiards, and I'll show that it satisfies a bound. In section 2.2, I'll explain coupled harmonic oscillators. So I have prepared 2 harmonic oscillators and weakly couple them. It's chaotic, it's known to be chaotic, and I can exactly compute this exponent C in the Lyapunov exponent by a scaling argument, and it says that it satisfies the bound. And I can even generalize this coupled harmonic oscillator to more complicated cases, and then bound is again saturated and satisfied. So let me start with the billiard. So this is the picture of the billiard. And normally people assume the Hamiltonian of the billiard is just p to the squared. It's a non-relativistic particle moving in the billiard. But let me generalize that to this general one, p to gamma, where gamma needs to be positive for the consistency of the motion. So in this general billiard, what is the Lyapunov exponent? So Lyapunov exponent as a function of energy is just proportional to the velocity. The reason is quite simple. If you put a particle and let it move, then it bounces on the wall like this and like this and like this. So how many times it bounces on the wall actually gives you the Lyapunov exponent. How many times it bounces on the wall in the unit time is proportional to the velocity. So the Lyapunov exponent is proportional to the velocity. The velocity is given by this formula, and from this Hamiltonian you get this. As a function of energy with this. And as you can see, this exponent C is given by this number, and which interestingly, needs to be smaller than 1. So the bound is actually satisfied. Then, next, let me consider a coupled harmonic oscillators. So this X and Y, these are harmonic oscillators, and I put a weak coupling between X and Y, degrees of freedom. If you look at the classical Poincare sections, it's a section of a phase space. And then if you turn on energy and make it higher and higher, then the Poincare section is given by all scattered plots. So this means that the motion is chaotic. At the low energy, it's regular, so non-chaotic. But at higher energy, it's chaotic. And you can numerically measure the classical Lyapunov exponent as a function of energy. And it goes like this. And in fact, these points follow the rule of e to the 1 over 4. And if you believe in this numerical estimation, then it satisfies the bound. But in fact, this 1 over 4 can be determined exactly by using the following argument. So at the high energy, in fact, the harmonic potential can be ignored. And the most important potential part is this coupling. So consider this coupling only in the high energy limit, and consider this simplified Hamiltonian. This simplified Hamiltonian allows scaling symmetry. T goes to alpha t, x goes to alpha inverse x, blah, blah, and the Hamiltonian goes to alpha to the minus 4 of Hamiltonian. And once you know this scaling symmetry, then Lyapunov exponent energy dependence can be read from this symmetry as follows. So this is in the exponent, lambda times t, and the lambda is a function of energy. And due to the scaling symmetry of this Hamiltonian, this needs to be equal to this one. So alpha is the scaling of time, and this is the scaling of energy. And since this SH is now minus 4 for this system, you can read off the Lyapunov exponent energy dependence, and it's 1 over 4. So C is equal to 1 over 4. This is a proof of this exponent. And from this argument, in fact, you can generalize a system to more generic ones and show the bound. So this is the very general 2D Hamiltonian, where X and Y are coupled by generic potential, and you can also modify the kinetic term like this. You can even consider a more complicated one, but at the high energy limit, with the change of variables, you can make the Hamiltonian to this form. And the consistency of motion actually needs this A and B parameters need to be greater than 1. And also, the boundedness of the orbit requires this M and M to satisfy these inequalities. So we need to use these inequalities. The scaling symmetry, which I argued, actually determines the energy exponent C like this. So this is quite complicated function of parameters A, B, P, Q, and M and N. But you can actually show that demanding these 4 inequalities, this C is always smaller than 1. So this is a non-trivial check of the bound. It's kind of surprising, since this conjecture was originated and motivated just by the well-definedness of canonical ensemble for out-of-time order correlators. But it seems that a classical system with very few number of degree of freedom satisfies this bound for any case. So this is the end of section 2. And I think I have 3-4 minutes. Do I have?
Yeah, you have 5 minutes.
Okay. So let me go on to the implication. So I prepared 4 slides. First of all, this is related to Professor Majumdar's question. The saturation is saturation of our bound is necessary for having black holes. And then I'll explain, in fact, the bound needs to assume 3 physically reasonable conditions for the Hamiltonian. And the latter 2 slides is for, are for the physical meaning of the bound and some discussions. Okay, let me start with section 3.1, saturation necessary for black holes. So let me remind you of what was MSS bound. This was for thermal ODOC, and the bound was like this. So here, temperature is here, and I think you would say that for a large number of degrees of freedom, temperature is almost equal to energy. So my bound is almost the same as MSS bound. And I think that's right. So for large number of degrees of freedom, from the standard argument which I draw here, the energy is always proportional to temperature with some coefficient gamma. Gamma is actually the in the definition of density of states here. So using this coefficient, energy is related to temperature. So if you apply this argument, then this temperature is almost equal to energy. So the Lyapunov exponent is proportional to energy, which saturates our bound. So this means that for large number of degrees of freedom, if you assume that, then saturation of our bound is necessary to saturate MSS bound. So it's necessary for having gravity description. So this is a relation to MSS bound and our upper bound. So let me argue the 3 physical conditions which I assumed to secure the bound. So first of all, the first condition is that Hamiltonian needs to be Hermitian to define energy. That's okay, right? And then second, when it is quantized, I need local time evolution. I think physical condition is necessary. For example, if you modify the billiard Hamiltonian to this very strange form, its Hamiltonian is exponential of momentum. So this is quite non-local. Then using this Hamiltonian, the Lyapunov exponent actually violates our bound. So this means that locality and the bound are kind of closely related somehow in the background. The third condition is that I need to require no infinitely small structure. So as you can easily guess, so if you have a system and if you put a very, very complicated structure as a potential of this system, then the Lyapunov exponent can grow infinitely large. But I have a bound. So what is the consistency in between these two? For example, if the potential is exponential of x, then this includes infinitely small structure in x, and it is expected that the bound is violated. And in fact, if you apply a canonical transformation which exchanges p and x, then this example goes back to this example, and it violates the bound. So in this way, I need physical 3 conditions. First, Hamiltonian needs to be Hermitian. Second, I need locality. And third, no infinitely small structure. If these 3 conditions are met, then we can have the bound I expect. I may skip this slide. Yeah, in fact, this bound actually means renormalizability for QFT. If you are interested, we can discuss. This is the last slide. So this is the implication of the bound. So how can we use this bound to argue something phenomenological in particle physics? This is one page of this famous book by Frogat and Nielsen. The title is Origin of Symmetries. This is a very interesting book. And if you look at this book, then there is an energy hierarchy, ground unification, quantum gravity, string, and then it leads to chaos. So somehow chaos may dictate what kind of symmetry is expected in the universe, and string theory and all of them can be derived from chaos. This is a picture in this book. And from the philosophy of this book, I can argue in the following way. The Lyapunov exponent is in fact equal to Kolmogorov-Shinai entropy, and saturation of Lyapunov exponent means saturation of the entropy. So it means that the fastest entropy production at high energy. So this means that if one has a quantum system which saturates my bound, then that bound generates a lot of entropy to dictate the universe. So in this sense, QFT saturating the chaos energy bound may be selected as the theory of the universe. Okay, so this is the end of my talk. So I wanted to advertise my conjecture to you, and I hope that I convinced you that this is true. And if you have any example which may violate this conjecture, please let me know. Thank you very much.
Let's thank the speaker for a very nice talk. So it's time for questions now.
Can I ask a question, please?
Please.
You see, your entire rationale for arguing that the bound exists is that you assume that there must exist a canonical ensemble in
That's right.
equilibrium statistical mechanics.
That's right.
Of course, the examples you considered, like a black hole falling in, like a particle falling into a black hole, you have made the assumption that the particle does not change the metric of the black hole, where in reality it always does. For instance, instead of a particle, if you consider black hole merger, then of course the canonical ensemble is not going to be valid. So there are 100 different ways in which the canonical ensemble idea of Maldacena et al. Can be violated. Therefore, I'm not sure that while I'm completely intrigued by your bound, I think it's a very interesting bound because it holds in so many examples. It must be true. I'm not convinced about its derivation. So I'm just putting it to you. This is more a skepticism. I'm not saying it's wrong, but I'm saying there are physical situations where canonical ensembles don't work. And the bound must therefore also exist in truly dynamical situations, right? Like
I agree with you. Yeah. So let me make a comment. So that's a very important point. And in fact, this conjecture is applied only to non-gravitating systems. Okay. So what I consider is only non-gravitating systems. The reason is that if you consider gravitational fields, then the Lyapunov exponent cannot be measured. The reason is that in gravity system, the time itself can be coordinate transformed into some other frame. And this means that the Lyapunov exponent has no meaning in gravitational systems.
Quite. I was getting to that. Very good point. Very good.
Yeah.
Yes.
So this upper bound for Lyapunov exponent only applies to the non-gravitating.
Okay. So maybe time for a quick question by one of the students.
Thank you very much. Excellent talk.
Well, chaos is measured by the out of time order correlation, that OTOC. But in the most of the cases in quantum system, we can calculate this by the numerical method. But in only for some few cases, like harmonic oscillator, we can calculate it analytically. Is there any other measures of chaos except that OTOC that we can compute analytically?
So that's a very good question. I think the question was about how to actually analytically compute Lyapunov exponent for generic systems, right? One thing is that if the system at high energy goes to a fixed point, conformal fixed point, which is non-trivial, then the Lyapunov exponent needs to grow as a, so Lyapunov exponent is equal to, sorry, this coefficient exponent C is equal to 1. The reason is that in conformal case, there is no other dimension for parameter. So the Lyapunov exponent, which has mass dimension 1, needs to be proportional to energy. So this is one consequence from this renormalizability condition argument for generic QFT, which I skipped. So so also for this case, some renormalization flow or some kind of symmetry protects the scaling, and then you can get the analytic expression for the Lyapunov exponent. But for other cases, I think it's quite difficult to get the Lyapunov exponent analytically. So what you can do is a numerical computation for classical cases, and for quantum cases, it's out of time order correlators, so it's more difficult.
Okay, so thank you very much, Professor Hashimoto. Very nice talk.
Thank you.
So now the next speaker is Amit Ghosh from Shah Institute of Nuclear Physics, and this is also an invited. We shall discuss here from Angular. So Amit. Amita, you can share your
Hello, can you hear me? Hello?
I think
If you want, then connect and then connect yourself. I can't hear you. Please disconnect and then connect yourself.
accuracy. So Amita, can you hear us?
We can't hear you.
We cannot.
Hello? Can you hear me?
Yes, yes.
We can't hear you. You can write your issue in the chat box.
Amita, you can share your slide.
You can write your issue in the chat box. We can't hear you. You can use any. Can you use any other device? You can use your phone. Okay, okay.
শুনতে পেলে? Can't get my microphone word. Okay. অমিতা জয়েন করেনি, এটাও মুশকিল। এখন জয়েনই করেনি, তাই না?
Mobile.
Professor Ali Shahia, are you?
Huh?
Yeah, Professor Ali Shahia.
Yes, sure.
Yeah. Can you hear me?
Yes, I do.
The next speaker was after Professor Hashimoto. It was Professor Amit Ghosh. He's having some error from his side. So will it for you to present it now?
Okay. That's fine for me.
You will get the full time. There is no problem. We can just reduce the time for today.
No.
And if it is okay for you, then you may start your presentation. So
Just now, or
yeah, you may start it now. So I will just quickly say. So the next speaker is Mohsen Ali Shahia from Iran, and he's from the Institute of Fundamental Sciences, IPM. And this is an invited talk for 40 minutes, and he shall be talking on holographic complexity with cutoff. So Professor Ali Shahia, it's all yours.
Okay, thank you very much. First of all, I would like to thank the organizer for inviting me, and I suppose have to share my desktop. And could you tell me how can I share my desktop, because it's the first time I'm working with this
Present now
computer.
It is the fifth button from the left.
From left.
Yes, sir.
I can't see such
Look
a
at the rectangle with the arrow. Rectangle with the arrow. Click on that.
So can you see the mic option?
I can.
শেয়ার করতে পারছে না
I have do I have ability of sharing, or you have to allow me to do that? Because
Sharing. You have to
Because I-
click on present now option. Then you have to select the entire screen.
my entire screen.
Then you have to click on the box, and then you will be able to share.
there will be a present now option coming there.
Is it sharing now?
No,
No,
sir.
it is not sharing.
You have to click on.
It is coming. It is
Okay,
coming.
okay, sir.
It is coming.
Yes, sir. You have to open your slides. Okay.
Yeah, it has come. It has come.
Please make it full screen. Okay, sir. Perfect. Okay.
Okay. Are you hearing me very clearly?
Yes, yes.
Okay. Let's thanks again the organizers for inviting me to give a talk. And actually, I'm going to talk about the complexity when the system has some cutoff. The talk is based on these following papers, which appears a few months ago. Let me start with saying some motivation of why we are interested in such a relation between quantum information and gravity. It is of great interest to understand the physics behind the horizon, though its understanding might require full knowledge of quantum gravity. Actually, asymptotic correspondence we have been using for more than almost 3 decades could provide a useful tool to explore at least certain feature of the physics behind the horizon. Indeed, working within this framework of asymptotic correspondence, the problem we are interested in maybe represents as how to construct a space-time from the boundary quantum field theory. In this context, holographic entanglement entropy was found useful to explore certain possibilities, though it might not be enough. To motivate why entanglement could not be enough, let me just say a few words, which is, I'm supposed to be well known for everybody by now, that in the context of asymptotic correspondence, we have the let's have an ADS black brane or black hole. Then the dual theory of this, the dual conformal fluid theory, is a conformal fluid at a finite temperature. Since the solution is static, the dual theory there shouldn't be any time-dependent quantity in the dual field theory. And according to on the other hand, according to asymptotic correspondence, everything, if it's correct, everything above should be given in terms of the boundary and vice versa. Now here is a puzzle. Let us start from empty space. Let's say asymptotic, the space is asymptotically ADS. And since the holographic dual is well defined in this case, let's start from empty space and just inject some energy on some matter there. And the process we inject in matter is a time dependent, of course. From dual tutorial point of view, is the thermalization system. Then when you are adding matter and at some point the black hole will be formed, which is somehow we are approaching the thermalization equilibrium. Now the point is that as soon as the black hole was formed, what we get this solution, the system is static, but still the volume inside the horizon keeps growing linearly with time. Therefore, there could be some time-dependent phenomena in the gravity side, and it should be understood from the field theory point of view as well. Actually, the boundary field theory, as I told you, when you are injecting the energy, reaches the thermal equilibrium, which is making a black hole very quickly, while the ancient Rosen bridge, which connecting two boundaries in the black hole we are interested in, go on much longer times. Therefore, there must be some quantity in field theory that correspond to this information, which is time dependent. That was the conjecture of Susskind, that the corresponding object should be holographic complexity. And it would be nice to understand the properties of the complexity. From field theory complexity, from field theory point of view, complexity is a bit tricky how to compute. From quantum mechanics, just one line definition is that you start from some reference set on you want to find the target space. The complex is the minimal gates you may have you can find to reach the target space. That's the definition of the complexity in quantum. In quantum field theory, it's a bit tricky, but in what follows, I just consider holographic description or graphic description of complexity. There are two different ways to compute the complexity. Proposal for concrete proposal to compute complexity. The one which is known as the CV proposal says that the complex of the boundary state is proportional to the volume of the maximal codimensional Box surface that extend to boundary and asymptotic to the time slice that on the boundary where the state is defined. There is another proposal for the complexity, which is known as the CA, which means that somehow we are computing on-shell actions on the certain region of the space-time, known as the Wheeler-DeWitt patch. And the Wheeler-DeWitt patch is a domain of dependence of any Cauchy surface in the bulk whose intersection with the asymptotic boundary is the time slice we are interested in. We want to compute its complexity. And these are two definitions of the well-known definition. There is some other, but there are well-known definitions of the definition of the complexity. In what follows, I will consider the second conjecture, which is a CA conjecture, and I will compute the complexity in this case. Okay, so we have to deal with the action. Action contains several terms to make the variation principle well defined or well imposed. And since you have the boundary, you have beside the bulk, beside the bulk part, you have several boundary Gibbons-Hawking term associated to space-time, time length, and null boundaries. Also, we should have some term associated with the join point when two boundaries intersect. There should be some term associated with this, and also to make it well-defined or remove some ambiguity, there could be some other counter terms, which I included here. There's a definition of gamma. Gamma is the term of the induced metric. Lambda is the affine parameter which parameterizes null boundaries. And also K1 and K2 in this expression is the normal vector associated with two boundaries which are intersecting. Using this action, I would like to compute this action in the certain part of the space-time, which is called Wheeler-DeWitt patch. And to do this, technically, you should put some cutoff here, and of course, at the end of the day, we send the cutoff to its proper limits. Here we have two cutoff. One cutoff is just UV cutoff. We put it to remove this infinity, UV infinity. And also we put some cutoff at near singularity, and then there in OR notation, the cutoff near singular should go to 0, and the UV cutoff should go to infinity. With this cutoff, now we should compute this on-shell action, each term in this action, and it is easy, it is straightforward to compute, and this is what we get for the growth of complexity, the derivative of the action or derivative of the complexity. And it's a constant, and it is known that the complexity growth reaches a constant at the late time, which is given by twice of the energy, which is known as the Lloyd bound. And if you look at this the way it approaches is constant, it approaches from above. And it seems that somehow in the gravity, the lower point is although at the late times, at late times approach is constant, but it goes from above. It means that it's violate the bound. But nevertheless, what we are interested in and what plays a role that it approaches a constant, which is given by the charge of the systems. Now let's put the system at the final cutoff. Let's consider the case when you have the radial cutoff and put some current and keep this, which means that to redo the same computation, but to keep this radial cutoff, which I call here, fixed and finite. There is indeed a good reason to say this situation, that it provides a holographic description for the conformal fluid to be deformed by certain deformation known as TT bar deformation. Although it is very nice deformation, although it's irrelevant, we are deforming the conformity by a relevant operator. Nevertheless, one can find the spectrum of the resultant theory almost exactly. And here for the particular case in 2 dimension, that's the spectrum you can find for this deformation. Its generalization to higher dimension has been done from point of view of the gravity, and it is done that the E plus 2 dimensional ADS black brane, or black hole you would say, solution with a radial cutoff could provide a holographic dual for a D plus 1 dimensional TT bar deformed conformal fluid theory. And which means that if you start from the solution I showed you before and put just a radial cutoff, then the dual theory has a deformation. And in this case, the energy, which is associated with the spectrum I told you in the previous slide, gets modified. And here is the exact expression for the energy for the deformed theory. So there is a very nice there's a well-defined theory, and it's interesting to understand the complexity for such a theory model as well. Now let's compute complexity while keeping the UV cutoff finite and fixed. And going to all computation, I just presented here. Of course, I didn't present the computation, I just showed you the result. And you get the answer doesn't change, and it is what you would expect, because at the end of the day, I send this UV cutoff to infinity, and just I remove all of this aspect of the UV. And this is what we expect, that the physical thing shouldn't be given on the cutoff. Therefore, this is what we get. And with this result, here is some observation. First of all, from gravity point of view, the holographic computed rules obtained by the on-shell action I just evaluated here in the relative patch is insensitive to UV cutoff at the late time. This is what I showed you, or I present here. On the other hand, from conformal fluid to the point of view, the late time growth is given by physical charges. This is what one would expect. It's not necessarily Lloyd bond, original Lloyd bond, but we would expect that in general ground, the complexity growth at the infinity is given by physical charges. And the physical charges depend on the UV cutoff, as I just showed you, the energy gets modified. Therefore, they are not consistent to each other here. Therefore, one may conclude either on-shell action does not compute complexity, or it does, but the late time behavior is not given by the physical charges, which is quite unphysical, or in our computation we need something. And this is the question I'm going to answer in the remaining of the talk. And okay, in what follows, I assume that the on-shell action does compute, and physically we would expect that when we add the cutoff, the physical charges will modify. Therefore, maybe there is something wrong with our computation. Therefore, I'm going to redo my computation more carefully. So let us start with our computation with the assumption that both cutoff I showed you, I told you RC, which is a cutoff at UV cutoff, and R naught, which is a cutoff at infinity, keep both of them fixed and finite. Then we do all of the computation. If you do this computation, here is what we get for the complexity from gravity point of view. You see that beside the term we have already found, there is some extra term which depends on the cutoff at near singularity. Therefore, the complexity from gravity point of view get modified. Now, if you want to compare it to a Lloyd bound, or to assume that the complexity should be given by the physical charges infinity, then here the energy, which we know that energy does also get modified, and here the modification of, and if you compare these two results, what we will get that there is a relation between the cutoff at the singularity and the cutoff at the boundary to make the computation consistent. Therefore, it means that as soon as one sets a UV cutoff at the boundary, the model enforces us to have a cutoff behind the horizon whose value is fixed by the UV cutoff. Actually, such a relation should be intuitively understood from the fact that the energy which Lloyd bound is given by the energy of the charge is defined at the boundary, while the latent behavior of the complexity entirely is evaluated from the action behind the horizon. Therefore, there should be some relation on the some object on the beyond the horizon and object at the infinity, and the cutoff is one of these objects. And this is an interesting feature of the complexity that has a potential to prove the physics behind the horizon. If correct, if this computation is correct, it somehow means that the near singularity modes may be regularized through the UV cutoff at the boundary. Now let's redo the same computation for charged black hole. What's happened with charged black hole? Yes, sure. Yes, go on. Yes.
Yeah, in 2 pages back, you argued that the physical charge may actually affect the late time behavior, but normally at late time, the low energy mode only appears in the physical observables, right? So any UV change may not alter the long time behavior for any physical observables. Complexity may be exceptional, but I actually missed your point.
Yeah. I agree with what you are saying. That what I'm saying that it rely on the fact that we would expect that the complexity is given by the energy or energy of the system. And since the energy get modified, we would expect that complexity should also.
No, I see. That's the point.
But
okay.
Yeah.
Thank you.
Okay, so. And okay, let's do the same for the charged black hole, and that's the simplest charged black hole. After charged black brane, where the situation is much more simpler than the black hole because of this special duration. And let's just do the same computation. Of course, the complexity for this model has already been computed in the literature, and here the latent behavior of the complexity of complexity growth. And now we want to put the cutoff in the system. There are two possibilities to put the cutoff here. Either we could put cutoff behind the inner horizon, because in the charged black hole we have two horizons. Either we could put the cutoff behind inner the horizon or between two horizons. And in what follows, we put the cutoff between two horizons, and we will see that it is the right thing to do. And going to all this computation, I am not presenting the computation here. And this is what we get for the latent behavior of the complexity when we have the cutoff in the charged black hole. Again, the complexity from gravity point of view is given by the cutoff, which depend on the cutoff, which is beyond the horizon. And this is what we expect, because as I told you, that the latent behavior of complexity entirely is given by the space that by the star which is behind the horizon. Now this has the same. If you look at this expression, this has the same form as that of the neutral charge case, and the charge dependence only comes from the blacking factor, which is if not. And it's then evident that it reduces to the neutral case if this one sense set charge to 0. On the other hand, if it has a, it is also clear that for R naught goes to R minus, which is inner horizon, it gives the known expression for the late-time growth of the complex of the charged black hole, which I showed you before. So if it is it is believed, okay, note that it is believed that the late-time behavior, as I told you, of the complexes should be expressed in terms of the conserved charges such as the energy. Therefore, there must be a relation between R naught for the charged black hole and UV cutoff RC, so that the above expression for the late-time growth of complexity can be written entirely in terms of the conserved charges, as we have done for such a. So the thing we should proceed by finding such a relation is again the Lloyd bond. Therefore, it would be nice to look at the Lloyd bond in the charged black hole. Actually, there are several conjectures for Lloyd bond in the charged black hole. Let's start from the some field definition of the Lloyd bond. The Lloyd bond gives you an upper bound on the growth of the rate of the complexity, which is given by the twice of the energy. And the late-time growth of the relative patch also, if you compute for the gravity point of view, you get also this the bond is saturated somehow, and you get this 2 times the mass of the black hole or the energy, which can be read as a statement of the saturation of the Lloyd bond. I should emphasize that although we are calling it Lloyd bond for the historical reason, more appropriately we should think of this as a bound on the holographic complexity from gravity point of view, which term of the conserved charges at the holographic boundary. In the presence of the UV cutoff, this would therefore be sensitive to UV cutoff. And if you look at the for charge black hole, there are some proposals which for the charge, when you have the charge, where here is the expression for Lloyd bond. Again, is the energy, and Q is the ADN charge of the system. And mu plus minus denote formally the chemical potential associated with the 2 horizons, inner and outer horizon. Of course, it's worth mentioning that although R minus cannot be interpreted the chemical potential physically from the conformal point of view, but at the end of the day, everything can be expressed in terms of the physical quantities at the boundary. Now, the saturation of the proposal should also be explicitly established or seen from the computation of the gravity, and it has been done that the bound saturates for the gravity point, from gravity point of view. And it is very nice to look at the way we get a neutral bound out of these charge cases. The limit on which we get a neutral charge is just sending Q equal to 0 and R minus to infinity, and at the same time, mu plus Q goes to 0 and mu minus Q goes to infinity. And if you apply this procedure of getting neutral black hole out of the charged black hole and look at the expression I have written here for the compressive growth, you will find that the contribution that you will see that the energy cancel from plus and minus, and the contribution these limits arise completely from the minus sign, which is associated with inner horizon, namely from the term which modified the original proposal of Lloyd bond because of the existence of the inner horizon. Somehow it's a puzzle here, because it is legitimate to expect that all such computation coming from inner horizon, where you will send this, you will want to get neutral black hole, should end up to 0, and everything should be given in terms of the outer horizon, which is a physical horizon. Therefore, there should be something fishy here, just using for this bound. To this in unnatural limiting behavior, it was argued in the literature that it is unable to accommodate the right expression for Lloyd bond when we have a cutoff in the system. Based on the above observation, we would like to propose a new bound for the late-time growth of the complexity. And here is our proposal. It has the same form, except that energy is multiplied by 2. Of course, if you apply for the non-result, because the energy cancel from our plus minus side, therefore you end up with the same result. But it has very nice zero charge limit, in the sense that if you go through this neutral limit, you will see that the minus part cancel goes to zero, and everything comes from this plus side. Of course, again, from the system which have been considered so far in the literature, we can see such a distinction because E plus and E minus in my notation are the same for all systems which have been studied here. But since we have the deformation, there might be a possibility that the E plus and E minus may not be equal. And indeed, if you go to this computation of how to deform the system when you have the chart, then get the result. E plus get modified, while E minus is remain unchanged. And also, you could also compute this, let's say, chemical potential, and put everything in this in the expression for Loipa. Is what you get here. And from the expression, it is clear that this minus side vanishes when Q go to zero limit, while everything is given by the positive, by the plus side. And in this case, it just reduces to what we would expect, which is the neutral case, and this is what I showed you before. Now, using this result, we can equate this expression of Loipa to what I have computed. I had computed from the complexity from gravity point of view, and equating this is what relation you get into UV cutoff and the cutoff behind the horizon. Now the question is there any other way to probe the behind the horizon cutoff and to see such a relation there? Note that one could also see for the small deformation, the behind the horizon cutoff. Maybe you can expand this this expression here and find some relation between inner and outer between the two cutoffs. Which is a very simple relation here. One observed that the two cutoffs come with different powers. Now the question, is there any way to understand this difference between R naught, which comes with power 1, and R2, which comes with the power 2? And to address this question, we know that in the context of ADS-CFT correspondence, there are several attempts to construct operators in dual conform operator to describe the inner horizon. One of them, which I'm going to consider, is the one which is given by the Papadopoulos and Baju, and just give you some very brief view on the relevant part of this construction. Is that let us consider free field in the field theory side, whose mode in the momentum space given by the O of omega and k. Then one may define a non-local operator labeled by the ADS radial coordinate R as follows. This is non-local operator in the conformity, but a local field on the top, with the proper function of F here. This operator has the same correlator as the free field propagated in the region denoted by 1 in this Penrose diagram of the internal black. We can similarly, one may define this another operator associated with the region 3 in this Penrose diagram, and also it has the same expression. Of course, F and F tilde are not the same, but nevertheless they satisfy Klein-Gordon equation here. Now the point is that in order to describe an operator behind the horizon, for left and right part of the Penrose diagram, we have the field here, one field here, and one mode here, and one mode here. But the interesting thing, in order to describe an operator behind the horizon, one needs both operators defined by O and O tilde to construct the field of behind the horizon. In other words, more precisely, for an operator behind the horizon, we need both modes, and this is the expression for the modes there, where G1 and G2 still satisfy the Klein-Gordon equation for the free field. Of course, there are some boundary conditions you have to match. I am not going to the detail of this discussion. Then the only thing which is important for us is that in order to construct operator behind operator which describing field behind the horizon, you need twice degrees of freedom than the one you want to consider the outside the horizon. Okay, in this context, intuitively, one would also expect that the setting UV cutoff, because the operator we are defined is non-local, would expect that the setting UV cutoff at the boundary would automatically restrict the range of the space-time accessible to the field defined behind the horizon, which is very reminiscent of the phenomena we have observed from complexity point of view. And to make this connection more concrete, let's consider the partition function of the field associated with those associated with the one which is the inner behind the horizon. And somehow we want to compute this partition function, rewriting this partition function in terms of the modes associated with two left and right region of the program. Some are at large and limit. When you have the generalized free field, then this partition function factorized, and somehow you get some relation between partition function associated with the operator behind the horizon and partition function associated for the field associated with the outside the horizon. And if you go to the ADS-FT correspondence and thus replace the partition function by exponential of the action in the classical limit for large, and this is the expression you will get that for the two action evaluated in two different region 1 and region 2, you get some expression. And to have the proportional, it's here the proportional to have some equality, it's better to compute the action for two different cases and just subtract them in order to get this equality. And if we apply this construction for the metric itself, linearized metric, and consider dual operator with the linear metric, when it's linear, then we will end up to computing the unshell action for the gravity itself, for the metric itself. And this is the expression for the action computed inside in region 1 and action computed in region 2, with and without cutoff, and just subtract this, and this is the expression for region 1 and region 2. And just plugging the expression I showed you that the exponential of the action in region 1 is twice of the exponential of the region. Sorry, e to the power exponential of the action in region 2 is twice of exponential action. Exponential of twice of the region 1. This is the expression you get. This is exactly the same relation we obtained from saturation of Lloyd bond and the complexity. Therefore, we somehow would explain. Somehow we are saying that maybe what we are computing is illegitimate. And from this expression, from the way I computed from this operator, now it is clear why these cutoffs come with the different powers. Because in order to describe inside the horizon mode, you need twice than those outside the horizon. Therefore, you would expect that the cutoff comes with different powers. Okay. To conclude, let me just summarize that although we have not fully understood the holographic complexity in the context of ADS as a correspondent, it seems that it's a useful quantity to probe the physics behind the horizon. In this context, we have seen that as soon as we fix a UV cutoff, we are in forces to have a cutoff behind the horizon whose value is fixed by the UV cutoff. For the charged black brane, the cutoff is between two horizons. It therefore indicates that emergence of the holographic censorship in bulk construction behind the inner horizon. And if correct, it means that the near horizon singularity, modes of near horizon singularity, may be regularized by the same UV cutoff we are using to normalize regularize the physics behind the horizon. The relation between UV and behind the horizon cutoff is consistent with the fact that to describe the behind the horizon, we need two copies of the outside the horizon field. And with this, I would like to thank you, all of the you, and to listen to my talk. Thank you very much. Okay.
Thank you very much.
That's all.
For a very nice talk. Let's thank the speaker. So, it's time for questions.
Can I ask
Sure.
a question? Nice talk, Professor Ali Shahiha.
Thank you.
The question that I had was that it seemed to me, and I'm not an expert in this field at all, I'm just curious, the definition of complexity is apparently independent of the coordinates you choose, right? It's a coordinate invariant definition. because it's in terms of the action which is coordinate independent. Is that correct?
Yes, yeah.
On the other hand, your cutoffs are definitely coordinate dependent.
Yes.
So if you change coordinates, let's say if you did the whole problem in the Kruskal frame rather than the Schwarzschild frame, would you expect different answers, different physics? If so, then I have a problem, right?
No. Okay. I agree with you that the complexity you are defining and you would cut off then this coordinate independent. But even in the complexity in the field theory itself, there's some ambiguity to have to define the complexity already in the quantum field theory. There are two ambiguities. One is to fix the cutoff there to field theory, and the way you want to define these gates from quantum mechanics. I'm talking about the quantum mechanics. Already in the quantum mechanics, there's some ambiguity to define the complexity. Is what I'm saying, and you would ask what kind of the ambiguity you may have in the gravity which should be associated with that complexity, and this is what people believe that the cutoff is one of them.
Yeah, of course. I realize that there's always an ambiguity in deciding what the cutoff is. But on the other hand, gravity, any theory of gravity would necessarily have to be general coordinate invariant, even at the quantum level. So when you're doing quantum calculations like you are, then I would expect that you'd have a generally covariant cutoff. Now, that's a huge problem in quantum gravity. So I'm curious how that problem is resolved here.
Well, the short question is I don't know, but yeah, but
well,
let me.
Yeah. Okay. So I'm just curious if there's an answer. Okay, no problem. I mean, I don't know is a very good answer. Thank you very much. Nice talk. Yeah.
But just let me to rephrase that what I told you about that complexity, even in the quantum mechanics, has some ambiguity to define.
Absolutely.
What I'm saying that somehow we would expect to get some ambiguity even in some well-defined quantum gravity. If you define it, which is a covariant invariant, even in this setup, you would expect to get some ambiguity to that.
Okay. Great. I think that's great. Thank you very much.
Okay, time for a quick question from one of the students. Hello, sir. While computing the complexity for using the complexity called action conjecture, the first given by Haskin in this paper, he just calculated by using the Einstein-Hilbert action plus the GHY term and the matter term, right? And
sir, I'm not hearing you. Sorry, sir, I'm not hearing you clearly. Could you?
In the complexity equal to action conjecture, the first paper by the Haskin. Can you hear me?
I'm trying. Yeah, just go ahead.
Oh, okay. Here the Haskin show that the complexity, the rate of change of complexity can be computed by using the Einstein-Hilbert action, GHY term, and the matter term. Okay. And he compute from there we can compute the rate of change of complexity. And the further computed by using that joint term and the counter term also. But at the late time, both the results are same. So why we should include this term? This is one question. And another thing is when we compute complexity, it basically probes behind the horizon, right? But when we have two horizons, such as the charged black hole or for dark black hole, then we integrate the actions between r plus to r minus, that is in between the horizon. We cannot probe further but about r minus thing. So, but
Okay. If I understood your question correctly, there are two questions. One of them is associated with the terms I added to, or people added to the action to compute the complexity. I think it's correct. It was your question. The significance of these terms.
yes.
Okay. The point is that in the original paper of Sasna, they just estimate somehow, I would say, the complexity rate. if you're going to compute it rigorously, you have to go to the all computation to compute the unselection. And it is a very important to define to say what do you mean by action, because there are some boundary terms and some joint and other terms that whether or not you have to include them or not. There is some principle which people are using, that whatever the action is, it should be it should have well-defined variational principle. And you can argue, you can go through the computation. If you exclude such a term, you are not getting a well-imposed action variational principle. Therefore, they are necessary to have. It is necessary to have this term in the action. Therefore, action is defined not by just bulk term, but with all terms which make it consistent. And this is also what we know from the holographic renormalization, that this boundary term plays an essential role there. Therefore, it is interesting. It's important to take all terms into account. And your other question, the other question which I forgot, could just tell me what.
The other question is, when we calculate that complexity from the action conjecture, we have to integrate that terms, and while integrating, we are integrating.
Okay, between two horizons. Well, you are not considered in the horizon, and that's an observation there, and it has to do with the a strong cosmic censorship that we just could probe the region which is a between two horizons, not outside the horizon. This is what our interpretation of this computation.
Thank you very much. Dr. Alishaya, are there any more questions? So if there are no more questions, then let us thank the speaker, Dr. Alishaya, for a very nice talk. Thank you very much. It's time for tea now. And we shall meet at 12:50. Next talk will be by Professor Amit Ghosh from Shanghai Institute of Nuclear Physics.
Sorry, what time are we meeting again, please? I couldn't hear that.
We are meeting at 12:50.
50?
12:50, 15.
Oh, 15. Okay. Thank you very much.
Yeah. Amita, you can hear us?
Can you hear me now?
Yes. Yes, I can hear you.
ক্লিয়ারলি, হ্যাঁ, শোনা যাচ্ছে তো?
একটু দেখা যাচ্ছে, অসুবিধা
আর
নেই।
স্লাইড দেখা যাচ্ছে তো?
দেখা যাচ্ছে।
ব্যাস ব্যাস, ঠিক আছে।
সোয়া 12টায় মিট করছি। সোয়া 12টা
হ্যাঁ হ্যাঁ, 12:15, ঠিক আছে। ওমা, হচ্ছে না তো, আর এইটাই ফিরে যেতে হবে। তাহলে আপাতত এখানেই থাকি, বুঝতে পারবো ওরা কখন শুরু করছে। হ্যাঁ।
So let us meet after the tea break. So after the tea break, the talk is by Professor Amit Ghosh of Shah Institute of Nuclear Physics, and he shall be speaking on black hole area from angular momentum. So Amit, it's all yours now. It's an invited talk of 40 minutes. Amit, can you hear us? Amita, can you hear us?
Hello?
Yes.
So you are ready?
We are ready, and this is an invited talk by Professor Amit Ghosh of Shah Institute of Nuclear Physics, and he shall be speaking on black hole area from angular momentum. Amit, it's all yours now.
You can see the screen, right?
And we can hear you also.
Okay. Okay, I'm sorry for the earlier incidents. So I will talk about black hole area from angular momentum. And the work is in collaboration with people I will show at the end. So let's talk about zero mass particles. And you can orient your Newman-Penrose frame so that the null vector L is along the momentum of the massless particle. The null vectors are normalized in this way. I'm sorry, they are not normalized, but the dot products are in this way. Other dot products are 0. They are all null. MM bar are complex. Now, given this choice, you can see that out of these Lorentz transformations, 1, 2, 3, 4, there are 6 Lorentz transformations. There is one is xi, one is theta. They are real. And C and D are complex, so there are 6 altogether. 2 and 3 keeps this choice invariant, so they preserve L. And these 2 and 3 form a subgroup, which is ISO2. The generators of this ISO2 are these 4x4 matrices. They are written in the Newman-Penrose basis, where I and j indices are run from 0 to 3. And these are the generators. R generates the rotation, P and Q generates the complex transformation. R generates 2 and P and Q generates 3. The algebra is very easy to calculate from these matrices. This is the standard ISO2 Lie algebra. And as I said, R generates rotation in the complex plane, and PQ generates the complex Lorentz transformation, which is a combination of rotation and boost. So this is the story about zero mass particles. If you want to talk about horizons, there are some major differences with massless particles. Mainly, there are 3 main differences. One, Lorentz transformations become gauge transformations. Other than p square equal to 0, that is the vector L is null, there are additional conditions which define the horizon. And obviously, because the space-time is non-trivial, there are connections and there are conditions on connections. These are the three main differences, apart from many other, from the massless particles. I will not discuss diffuse in this talk, only Lorentz transformations. Now, it is not obvious that there exists a subgroup of the Lorentz group that would preserve these additional conditions. It is also not obvious that the subgroup of the Lorentz group would be bigger than ISO2. I will show that it's actually ISO2 semi-direct R. And a horizon would spontaneously breaks the Lorentz group to a subgroup. Now to understand the last point, that how does it break spontaneously to a subgroup of the Lorentz group, take the example of a complex scalar field phi given by a pair of real fields phi 1, phi 2. If the potential is a function of the modulus of phi, then obviously there is a rotational symmetry in the phi 1, phi 2 plane, the complex field plane, and it's a continuous global symmetry. Now, if you pick a solution where the complex scalar field phi is a real value v, then it breaks the global symmetry spontaneously, because it's a symmetry in the complex plane. So you pick a real solution, then it obviously breaks the symmetry spontaneously. We can couple the phi gauge field to a complex to a gauge field, and then the global symmetry, global rotational symmetry becomes a local symmetry, along with the transformations of the gauge field. And then obviously the same solution breaks the local symmetry spontaneously instead of the global symmetry. And it is well known that in quantum field theory, these kind of things lead to well-known phenomena like Goldstone's theorem and Higgs mechanism. Now, coming back to horizon, we will stick to a special class of horizons, which is called non-expanding horizons. I'll go slowly here. A non-expanding horizon is a null hypersurface which is generated by smooth null vector fields, by a class of smooth null vector fields, not only one L but class of L given by f of L. F is a smooth function on the null hypersurface, and it is topologically sphere across R. And all these vectors in the class, they are geodesic vectors, and they have zero expansion. So these three properties mainly define what we call non-expanding horizons. Now, why they are important, why they are relevant at all in gravitational physics? The reason is that these properties are satisfied by all event horizons of all known exact solutions of black hole solutions. And they generalize Killing horizons, because in defining the Killing horizons, you need to assume certain properties in the neighborhood of the horizon. There is no assignment of properties in the neighborhood. All the three properties are intrinsic to the horizon. So all the Killing horizons are non-expanding horizons. The opposite is not always true. Now, what follows from these conditions is that the connections, some which call NP scalars, Newman-Penrose scalars, are zero. In particular, kappa, Newman-Penrose, rho sigma, these three NP scalars are zero. These are special connection coefficients. For example, sigma is the m bar component of grad A LB, and rho is the mm bar component of grad A LB, and so on. And it also follows that in our geodesics FL, they are both shear and twist free. Now, coming back to the spontaneous symmetry breaking aspect of the non-expanding horizon, let us compare the zero vanishing of this scalars, NP scalars, with taking a particular real solution phi equal to V. You can show that any solution for which the above Newman-Penrose scalars are zero, they break the local Lorentz symmetry spontaneously. The reason is that if you get back to the Lorentz transformations, under 1, 2, 3, the first three Lorentz transformations, these Newman-Penrose coefficients transform homogeneously. And under the fourth Lorentz transformation, these connections transform non-homogeneously, and therefore the symmetry is spontaneously broken. The fourth transformation is broken. If you calculate the unbroken transformations, the generators of the unbroken transformations, they turn out to be the old ones, RPQ, and the new one, B, the matrix B, which generate the scaling transformation of the null vector L. And they form the RPQ, the old RPQ form the ISO2 Lie algebra, as we have already seen for the case of massless particles. Along with B, they generate the semi-direct product of ISO2 cross R. It's semi-direct because of the commutation relations that B satisfies with the rest of the ISO2 RPQ. So B is the new symmetry, unbroken symmetry that arise in this case. Now, to understand this symmetry, this additional R, which is generated by B, as I said, it generates the scaling transformation. It is a symmetry that was not present for the case of massless particles, because a massless particle with a fixed energy momentum does not allow rescaling. You have a fixed 4 momentum. And even if you take a global horizon here, global solution here, global black hole solution here, exact black hole solution, it does not allow rescaling of L, simply because the asymptotic time fixes a particular L on the horizon. However, if the solution is not globally known and you only describe the horizon by its near horizon behavior, then it is not possible to fix the normalization of L completely, and therefore this additional symmetry arises. This is the reason why the symmetry increases from the case of massless particles. The full implication of this symmetry breaking in gravity, in particular its effects on quantum gravity of black holes, is not quite understood yet. Now let us get back to the main part of the talk, which is symplectic geometry. For asymptotic observers, the interface, which is the null surface here, the horizon, it's actually a boundary of the space-time. The reason is that the horizon, which is S2 cross R, the sphere, S2 part of it, becomes a trapped surface. And therefore, the interior of the trapped surface is causally inaccessible to asymptotic observers. And therefore, it becomes a boundary of the space-time. So for these observers, the symplectic geometry is basically based on a manifold with a boundary. And it is well known for many years of work that for this particular geometry and for Einstein-Holst action, there is a pre-symplectic structure that exists. By that I mean that you have a pre-symplectic structure that has a bulk part, which is given by integration over the volume. And there are two boundary parts, because the hypersurface cuts the interface at a sphere S, and also cuts the infinity at a sphere S infinity, and there are appropriate boundary terms. So all these terms can be calculated from the Einstein Hall action, and it can show that it exists. It exists in the sense that the pre-symplectic structure is actually independent of the choice of the hypersurface sigma, and also the cuts on the horizon and null infinity or space-like infinity. Now, given the symplectic structure, the Lorentz group generators that we talked about, ISO2 cross R, the unbroken symmetry, they manifest as Noether charges or Hamiltonians or some Hamiltonian vector fields in the bulk of the pre-symplectic structure, in the bulk part of the symplectic structure. However, the bulk part, the charges are all zero. The Hamiltonians are all zero on shell because the first class nature of the constraints. These are all gauge transformations. Therefore, I will only discuss about the boundary part of the pre-symplectic structure. And if you calculate the transformation where xij are the generators of the Lorentz group, in particular xij will be those, the unbroken part of the Lorentz group, you will find that the boundary symplectic structure gives you this contribution. There's a gamma that is coming from the Holst action. There's a part which is depending on gamma, and there is a part which is independent of gamma. The part independent of gamma involves a particular two form, which is sigma ij. And EI, etc., they are tetrads. So if you take the particular generators that we introduce BR, PQ, and put in here, you find that the BR charges are non-zero on the horizon, and they are both proportional to the area of the sphere, while the PQ charges are zero on the boundary. So BR charges are obviously all charges are zero in the bulk, but they are non-zero in the boundary, and PQ are zero in the boundary. Furthermore, it follows that the B charge is gamma times the R charge. There is a relative gamma factor because the B charge arises from the gamma independent part of the symplectic structure, and the R charge arises from the gamma dependent part of the symplectic structure. Obviously, there is a relative gamma factor. Now, this relation is not new. Such a relation has been found independently earlier from spin foam models of quantum gravity. References I have given in the last transparency. If you calculate the rotation charge, then it turns out to be the area of the sphere, its value turns out to be the area of the sphere, to sphere, divided by 8 pi g gamma, and there exist representations in which this R charge is actually half integers. Now, this is also not a new relation. This relation was found from loop quantum gravity, from the spin network formulation of loop quantum gravity, where the area spectrum is known to be 8 pi g gamma mod of j, where mod of j is the square of the angular momentum generator, whose the j square spectrum is j into j plus 1, where j is precisely of this form, half integer values, and there is a h cut because it's a quantum mechanical calculation. This is a quantum gravity result. So this can be compared with this classical result here. Now, what we have found here from the very simple classical analysis are quite remarkable for two reasons. Number one, we did not use anything more than elementary classical physics and Einstein-Holst action here in this calculation. And number two, many deep results are following from this analysis, which otherwise need additional structures. For example, you have to assume spin foam models of quantum gravity or spin network models of quantum gravity to derive. So therefore, these results earlier were thought to have purely non-classical origin. The fact that this can be derived from simple classical physics is quite remarkable for this particular reason. However, for us, there are many things that are to be understood from here. For example, if we quantize the rotation generator, we get a spectrum of area, which, as I showed you, broadly agrees with the spoon network result, but disagrees in detail. For example, in our calculation, you don't find log corrections which were there in spin network calculations. Question is that, can these relations be extended to all rotational generators? And there are many more. Especially, we found that some charges like PQ have zero boundary values, while charges RB have non-zero boundary values. Why is that? Now, if you compare this with, for example, other boundary values of charges like the Bondi energy or Bondi angular momentum, which are charges defined at null infinity, in particular future null infinity, non-zero values of Bondi energy and angular momentum signal existence of radiation at infinity. So there is a physics behind whether a particular charge is zero or non-zero at a boundary. What is the physics in this case that BR charges are non-zero while PQ charges are zero? There is another example that non-zero ADM energy angular momentum, which is defined as space-like infinity, it signals some non-trivial space-time physics or existence of some particular type of matter in the space-time. So there is also a physics involved that a charge is zero or non-zero. So the question is that what do non-zero values of RB mean? Now, we have already done some analysis regarding the B charge. We have seen that the B generates the local class FL of horizons, and some calculations show that if you want to go from one member of the equivalence class to another member, this may require some energy fluxes to flow tangential to the horizon. So they are energy fluxes as close as you can imagine to the horizon. They are just not falling inside. So they are not spoiling the isolation of the horizon, but nevertheless may induce a non-zero boundary value of the B charge. The boundary value of the R charge is not quite understood yet. What does it mean? What does it refer to? This is in particular connected to the area spectrum. So I will stop here. Here are the references. The symmetry part was calculated in this reference. The first references, the other part of the work was calculated in these papers, particularly the last one. And earlier results were found in some other works. In particular, the B charge was the physics of the B charge was analyzed in this paper. And here are some reviews if you want to look at regarding the background literature in this subject. Thank you very much. I'll be happy to answer questions.
Time for question. And we can keep
Can I answer?
further-
Can I ask a question, please? Nice talk, Amit. But it was sort of reminiscent of our discussions at the Saha Institute 10 years ago. Of course, this part, as you correctly pointed out, the business about the R charge, etc., is sort of newly formulated. Now, I noticed that you said that the area spectrum does not quite agree with the quantum area spectrum. Of course, the way you formulated your algebra, the symmetry algebra, this is a classical algebra, perhaps including Lie derivatives and so on. So it's a classical algebra, and it stands to reason that when you go to the quantum situation, the algebra will be modified, perhaps by a C-number extension. And then, of course, you will get perhaps the kind of agreement that you are seeking. Is that possible? That's the first question. And I have another question. Have you thought about dynamical horizons? What would happen there, for instance? Thank you very much.
Yeah, what will happen in the see, we are yet to quantize the gravity part of the calculation. So it's not clear that how these charges will be quantized. And as you say, that it's possible that the algebra has a C correction, central extension.
Right.
And in that case, log correction will reappear.
Yes.
Also, we are trying to because the other part of the symmetry is only spontaneously broken. So the theory remains invariant under full SL2C, and therefore it's possible that the full area spectrum, area angular momentum relation can still be recovered from purely classical physics. The reason we are quite excited about is that the classical physics gives you so much. You don't have to go to fancy quantum gravity models and assume anything regarding the Hilbert space and other structures to really talk about relations which have roots in classical physics. And once we have found some roots in classical physics, it's very hard to deny that.
Oh, no, there's no denial.
Yes. And secondly, yes, of course, that what was the other question?
About dynamical horizons.
Yes, actually, in this work, with Oviru, we little bit looked into the dynamical, slightly dynamical part, but so there is an energy flow tangential to the horizon, but it's not fully dynamical. And we tried to generalize it to dynamical horizons, but didn't quite work out that way.
I see.
So maybe some other, there is some deep physics that we are missing. That could be the reason that it doesn't quite work out.
Okay, thank you very much.
Yeah, Amit, can you hear me?
Yes, I can hear you.
Yeah. So I don't know if you may have already mentioned this during your talk, and so I have a couple of small questions. One is, can you include the cosmological constant?
Sorry?
Can you include the cosmological constant in your calculation?
Yes, I mean, if you introduce the cosmological constant, I don't think that the other parts that in the existence of symplectic structure, etc., will be affected.
But the nature of black hole will be affected.
Sorry?
The nature of the black hole will be affected.
Yes, sure. Yes, that is true.
The other question.
But we are not really talking about any particular solution here.
No.
So the features, what are the broad? We are only looking at the broad features of the horizon and its properties. So if if the black hole solution in presence of the cosmological constant still satisfies these properties, which I think they do, then this analysis will go through.
A related question is, hold if your black hole is not asymptotically flat.
Yeah, so that's the power of this exercise, that we have not really assumed anything about the asymptotic structures. Because if you fix the asymptotic structures, then this class of this normalization, this scaling class may disappear.
Right.
So the fact that we are only looking at the near horizon region, so it doesn't matter whether a solution is asymptotically flat or not. See, these are very local relations, that the R charge is related to the area of the horizon, doesn't require anything to assume about the asymptotic structure of the spacetime.
Okay, maybe we'll discuss it.
Does that answer your question? Sorry,
So,
Amitabh?
yeah, that is fine.
Okay.
So, Golam, you can go ahead.
Okay, thanks. Amindat, thank you for the talk. So I have a rather naive question. Can
Please.
you hear me?
Yes.
So I mean, somehow you're presuming that there is a horizon, right? From the beginning, the calculation. So in a real life situation that we see, I mean,
Yes.
a black hole is formed from some collapse of dust
Yes,
cloud or
yes.
something like that.
Yes.
So is that possibility? Those type of black holes are sort of excluded from the kind of
Which kind of black holes?
So those are like forming at a certain instant.
Oh, this is the dynamical horizon you are talking about.
Yeah.
That is the question actually Parthoda was raising.
So can you also generalize your approach there?
Getting formed, its horizon is increasing.
Yeah.
That is a dynamical issue. And we haven't quite extended this part to dynamical horizons.
Okay. But I mean, you're hopeful that it will go through.
I think there are some deeper issues that have to be included. Just this structure, this bare structure will not be extended.
Okay.
Because I'm not sure what are the symmetries of the dynamical horizon. What symmetries will be broken or unbroken. That analysis is not known to me.
Okay.
And also there is a deeper issue, that whether there exists a symplectic structure. That part is that is the most difficult part.
So it may not even go through. That's what you're saying.
Yes. So more work is needed in the sense that one has to prove that there is a symplectic structure with the boundary conditions that a dynamical horizons need. That part is not complete yet. We tried, but it didn't quite go through.
But Amit, sorry,
Yes.
following up on that issue, I just want to comment that you're using the covariant phase space formalism.
Yes.
Right, and that should go through. There should be still symplectic structure.
Oh, the symplectic structure. No, the symplectic structure, nobody has really shown that it exists. See, one needs a symplectic structure which is independent of the hypersurfaces.
Absolutely.
Now, but that in a dynamical situation is not being done. And actually there wouldn't be quite independence. See, the independence of what should I say? The independent of the hypersurface choice of hypersurface is actually, it's not applicable for the dynamical case, because there would be some difference in the choice of more matter goes through in each hypersurface. So if you look at hypersurface wise, then more matter will go through as we evolve, right?
Yeah, I understand if you look at it from that point of view, but that's
So,
the whole point of doing.
yes.
That's the whole point of doing covariant
No,
phase space.
covariant,
Look at
but
the
no solution. But the question is that what is the definition of, what would be the appropriate definition of independence of hypersurface that has to be reformulated? Because there would be dependence. Still, I mean, what kind of consistency condition would be required? That is not fully understood.
Yeah, maybe if you did something like a Vaidya calculation with a Vaidya space-time, just to see what it is, throw some light on this, right? Because Vaidya has a dynamical horizon.
Yes, I mean, that is, see, solution would be a difficult issue. Difficult issue would be that what will be the consistency condition on the symplectic structure. See, if nothing is changing, if it is completely isolated, then you can say that one hypersurface doesn't make a difference from the other hypersurface. So physically, it makes sense. But in the case of a dynamical horizon, when the black hole is absorbing matter, then physically you would expect changes. So then the issue of hypersurface independence would be slightly different.
Yeah, I understand the difficulties, but okay, anyway, thanks. Very nice. Yeah.
Okay, so if there are no more questions, let's speak once again. And we're going to take the lunch break now. We shall meet at 5 minutes past 2.
Okay, thank you very much.